This second session will focus on the processing of biodegradable plastics. During the lecture, you will again have the opportunity to ask your questions, so please feel free to join in the chat using the chat function or the microphone on site. You can also write your questions there, which we will then be happy to forward to the speakers. So now we return to the scientific part of the Congress, and I would like to introduce our next speaker. Dr. Sebastian Heßner holds a PhD in plastics processing. Since 2011, he has been working as a pilot manager for Evonik. Today, he heads the application technology for compounding additives, which are used in a variety of processes and applications. Current activities focus on recycling, packaging, e-mobility, and biopolymers. His motto is, "Plastics offer so many possibilities that can be multiplied with the right additive." Please welcome Dr. Sebastian Heßner from Evonik Operations GmbH with a presentation on additive technologies for bioplastics. Welcome.
Yeah, thank you for the kind introduction, and I think my task is now after the lunch to help you to overcome the food coma. And yeah, I will start with a small story. When I heard about that Vietnam is the partner country, I talked to my neighbor who is Vietnamese, and yeah, I want to welcome you in your Vietnamese language, and I asked him if he can help me with a little sentence, and yeah, now I will try to welcome all the Vietnamese, like he told me. It's Toi Sin, Gua Loi Chao, Torkaban. Yeah, I hope I pronounced it a little bit in the right way. Is there some Vietnamese who can confirm this? No? Okay. Yeah, so we'll start with my presentation now. And yeah, this is about additive technologies in bioplastics. And I start with a slide I think the most of you must know already. And it's about the differentiation between the bio-based and the biodegradable polymers. And when we talk about additives, we approach both of these groups, also the bio-based and the biodegradable polymers. And our idea is to develop a portfolio of additives which are also bio-based and biodegradable. And on the right side, you see already some pictures of some bio applications where we worked on in the last years, and where I will give some ideas and results what we generated in the last years. Yeah, the department I'm working for at Evonik is the application technology, and yeah, in my department we have a pilot plant with most of the plastics processing possibilities our customers are using, and our idea is to support our customers as good as possible, and therefore we build up know-how in a lot of different applications, and yeah, especially for flame retardant polymers and scratch resistant polymers and dispersing of fillers, flame retardants and pigments, and yeah, to evaluate the properties of the plastics we have in our lab a variety of yeah, equipment to evaluate the properties. And yeah, as already said in the introduction, we are now focusing on recycling, packaging, e-mobility, and biopolymer topics. And yeah, therefore I will come to my agenda after this short introduction. At first I will introduce you to our additive technologies, and then in the main part of the presentation I will show you some results from the research projects, the Tech Plastic and the Reksha project. And at the end of my presentation, I will say a few words about our activities regarding plastics recycling, and at the end, a sustainable approach of a PPA for filmmaking. Yeah, starting with a view of our activities, we try to approach the whole process chain, starting with the raw material manufacturers, and this could be the polymer manufacturers, but also the filler manufacturers. Here we offer solutions, for example, like a surface treatment for a pigment to make it more compatible to the polymer. And the main customers are master batchers and compounders, where we have a wide portfolio of processing, but also performance additives. And since a few years, we enhanced our portfolio with our Aquarel portfolio for the converters, where we approach molders and especially filmmakers that they can add a certain value to their product, like an anti-fogging aid, for example. And what is most important for us is that we are in an intensive exchange with the tiers, with the customers, to get a deep knowledge what are the market needs. Yeah, regarding the additive technologies, we divided today in 4 groups. The first group are the so-called organic modified siloxanes. So this is the specialty for our site in Essen, that we produce siloxane materials, and the specialty is the organic modification, which can be adjusted in a wide range, and that we can offer different effects with this product group. Yeah, the second big product portfolio group are the organic-based dispersing aids. So that here we have no siloxane backbone. Here we have a polymeric backbone, where we add hydrophilic and organophilic groups to have a compatibilizing effect. And this is the second group. The third group of additive technology we offer is a so-called odor absorber technology, which is mainly used for recycled polymers. And the fourth group I'm talking about is the so-called Aquarel technology, which is a sponge-like porous polymer, and this is not one polymer, so we have a portfolio of a wide range of polymers, and the specialty is that we can produce, based on these different polymers, master batches out of liquid additives to turn them into solid ones. And this is the first overlap with the bio-based or the bioplastics topics. Here we offer 2 grades, which are based on the one hand on PLA and on a biopolyester. And for you as processor of biopolymer materials, if you want to add an additive and it's liquid and you want to turn it into a solid one, because a solid one is more easy to feed, we can offer you to turn this special liquid additive into a solid one based on these materials. And the last years we were working together in funded projects with our customers, with research institutes, and the first project I want to talk about was the so-called Tech Plastic project, where we want to turn PLA into an industrial material and to overcome to give the PLA the flame retardancy, heat resistance, and a certain impact strength, which is needed for an industrial application. And the second project we'll talk about is the so-called Reksha project, where we try to incorporate natural fibers into a biopolymer. Yeah, starting with the first one, so PLA is widely used as a polymer for packaging applications. With its good chemical stability, it's easy to process, has a high mechanical strength, and is already good commercial available. But for an industrial use, we miss the flame resistance. It's brittle, so we miss the impact strength. And yeah, even the temperature, the heat resistance is not given. And so we had the idea to add flame retardants, impact modifiers, nucleating agents, and at all the Evonik additives do not offer this effect itself, but help to level, to balance the properties, to improve the processing, and at the end to have an overall property. And we did not add only these ingredients, but we had also looked to the processing, and there we looked at both an isothermal crystallization and also a variothermal injection molding process. Yeah, when we talk about impact strength or flame resistance, it's easy to add a certain additive, and but when we talk about the heat resistance, it's more depending on the morphology of the compound. And if we have a look on the left side, we see on the upper side it's a short cooling time, and on the lower a longer cooling time, that we increase the crystallization with longer times. And when we now add a low content of flame retardant, we see that we have even at at short cycle times have a crystallization, but when we now incorporate more flame retardant, we disturb this crystallization. And so we see already at this point that it's difficult to reach all the properties we need for the industrial use of the PLA. And regarding the heat resistance, it's beneficial to process the material at a higher temperature, so at around about the glass transition temperature. And if we increase the mold temperature from room temperature up to 110 degrees, we can double the HDT value, so the heat resistance is higher, but even the cooling time is rising extremely. And therefore we had this approach with a variothermal processing, injection molding processing, that we had the chance to reduce the cycle time down to from 90 to 70 seconds, and even lower it down to 55 seconds, and maintain the heat resistance at around about 100 degrees C. Yeah, at the end, we have to state that it's difficult to reach all these three values in one recipe. So if we start with a PLA in the middle, we try to reach with the first compound all three properties, but we see that we did not reach the flame resistance good enough, and then we optimized step by step. But it was not really possible when we now have a look to this red target triangle to reach all properties in the same way. So we need to focus on the needed properties. Yeah, within the Raksha project, we talk about the industrialization of natural fibers and biopolymers, and with the example of this child safety seat, we approached this topic, and in the next slide we see what was the responsibilities and the contents of this project. So we used flux fibers and wood fibers in the first step to improve the processing of the first semi-finished products. We did there a coating, for example, of the fibers. And as biopolymer, we used the Evonik polyamide 1010, and both bringing together. On the one hand, we developed a VPC recipe and UD tape, and determined the material properties. And in parallel, we came from this state-of-the-art geometry from Britax Römer, from the child safety seat, and adjusted the styling and had a construction which was composite conform, and could then go into the tool design and tool making. And out of these UD tapes, we produced a laminate, and this was taken by a handling system into a hybrid injection molding to produce these bio-based and natural fiber reinforced child safety seat. And at the end, we had a validation, first virtual, and then what is not done yet, we want to do a physical validation with a real crash test. Yeah, from the process, the hybrid molding process, in the first step, we will take the laminate from the stock, heating it up in an IR oven, then positioning it into the mold, closing the mold, and then the shape is formed. During back injection molding, the full form will be molded, and then we have the possibility to eject the sheet, the seed shell. Yeah, this is the machinery, and on top this IR oven, which we used for producing this demonstrator. And here you have an insight into this mold where we produced this the sheet shell, and this is the final product at the end. Yeah, now I come to the second part of my presentation, or the final part of the presentation, where I want to say a few words about the recycling approach. So we help to make circular plastics happen. And the first step is, like we heard this morning, to reduce waste. And we will help the filmmaking industry, for example, by using our new processing aid to reduce startup waste, for example. Then we build up a product portfolio for the mechanical recycling that we can make out of this process chain, a process circle. And at the end, we help a little bit during decomposing with our biodegradable additive portfolio. Yeah, here you can see a typical processing of this mechanical recycling, starting in the beginning with a shredded and sorted, pre-sorted material, which is washed, and then we have this so-called zinc float bath, where we can separate by density, and then you have a drying step, a pelletizing step, and at the end a compounding step. And in these different steps, we have the possibility to improve this processing. For example, during the washing step, there we have wetting agents for a better wetting, that we improve the separation, that no air bubbles stick on the light material, on the heavy material, that it's float up. And during the washing step, we have additives for so-called de-inking, de-labeling, demetallizing, what we will see in the next slide as an example. And during pelletizing or during compounding, we can incorporate additives for malodor absorption and compatibilization. Yeah, here you can see some examples that ink really can be removed and yeah, to have a more clean recycling stream, and even metallization can be removed, or some labels. And with the dewatering, we have one additive which is also biodegradable, that we have no wastewater contamination, for example. And then we can reduce the water content to save thermal drying energy. Yeah, here's one example with where we processed an agricultural film by using our odor absorber, that we have a significant improvement of this smell of this recycling stream. And there we have not only a product for compounding, but also now a product for single screw applications. Yeah, here a short view on one example, how we try to compatibilize recycling streams. And yeah, for example, here we have a contamination of an HDPE with PP. And yeah, here we can improve the elongation significantly, that it's not so brittle. Yeah, at the end, my last two content slides, I will give or say a few words regarding the processing aid, which we already tested in a big trial at our machine manufacturer Reifenhäuser, where we produced a multi-layer film with a high throughput of 500 kg per hour, 30 micron thin and almost 3 meters wide. And the idea behind is that we have here an OMS-based polymer processing aid, and we have the chance to replace the fluorine-based PPAs, especially in the US. The fluorine-based materials are already forbidden, and yeah, we have all in all a 2-in-1 approach, PPA plus a slip enhancer, and the main focus is to reduce or to remove or to avoid shark skin and dye build-up during the production. Yeah, I think with a closer look to the time, I'm a little bit over the time, I can summarize that I first talked about our additive portfolio, then the enhancement of PLA for technical application with higher heat resistance, impact strength, and flame retardants. And in the second project, where we worked on the natural fiber reinforced bioplastics for the automotive application with high mechanical demands, and how we support the circular economy with our partly biodegradable additives for washing, odor absorption, compatibilization, and at the end, the solution for packaging, for the packaging industry with our sustainable polymer processing aid. And yeah, here of the acknowledgement for the publicly funded projects, and I added one slide with my contacts. If there are questions after our session today, that you can contact me as well. Yeah, then thank you for your attention, and if you have questions, you're welcome.
Thank you very much, Dr. Sebastian Heßner. Thank you. So you are invited to ask questions, if you have any.
I see there are no. You're shy after lunch, guys.
Okay.
But there are some of the digital audience, and one of the questions was regarding your flame retardant projects using PLA. Have you also tested and investigated other biopolymers than PLA in that project, or is it a kind of focused look into others?
So in this project, I think it's regarding the tech plastic project. We are focused on just PLA, And yeah, then there we had these 3 demands: flame resistance, impact strength, and heat resistance. But we have a knowledge about a variety of polymers regarding flame resistance. So we are working for a long time, for example, for the cable industry to improve the flame resistance, and also the processing. Yeah, so in this project, no, there we focus on the PLA. But in general, we have the knowledge regarding flame resistance or optimizing flame resistance of other polymers as well.
Okay, thank you. There's a second question regarding your other offer of cleaning of plastics in the mechanical recycling. Have you also a kind of additive to recover flame retardant additives like APP in that process, which are phosphorus based?
Yeah, not really. So with this, in this cleaning step, we are today focusing on the cleaning of, for example, the shredded material out of the yellow bag, and not explicitly for this flame retardant materials. But we are talking about, and then it's a question how to collect this material in the right way, and how to work with the material later on.
I have a different question to you from myself, if you allow me, from the audience. It's regarding also your first project, the E&E switch in building and construction applications. We all know that the next regulation after automotive will be building and construction, CO2 reduction in those kind of industry. How is the reaction of the industry providing switches and plugs and electric devices for building and construction? How was the reaction? Are they already preparing for that, or is it too early, or was there any?
No, I don't think so. So we had on board in this project consortium the producers of these plugs, and they are really interested in have a change to biopolymers. And so we had not only not only in this project this approach, but now we will have a follow-up project with other participants which are also interested. So I think this is a really interesting topic for this market.
Thank you very much, Sebastian.
You're welcome.
Thank you very much for the interesting lecture and answering the question.